Hi, this is Jeff Coronado on behalf of JCSE, and this is Bridging the Gap. So it's a series of structural engineering design tutorials that we have here at the office that we use to assist young structural engineers. And by young, we're talking about either for those of you that are maybe in your junior or senior year of school, perhaps in graduate school, looking to get into industry within the next year or two. For those of you, you know that finding a job in structural engineering is real competitive. Obviously, there's way more civil engineers coming out of school than there are structural engineering positions. So if you're looking to get a head start on your career, something that will give you some traction that will assist you in then possibly securing employment in structural engineering, or for those of you who are were fortunate enough to obtain a position in structural engineering, and you're within your first few years of practice, you know that there's quite a gap between what industry expects you to know and what you were taught in school. So these tutorial sessions are intended to aid both of you in making that transition from school into industry. If you find this tutorial helpful, sure would appreciate you giving us a thumbs up at the end. Any comments, any suggestions that you have at the end, also please leave them after the tutorial here. And if you find the tutorial was helpful to you, then by all means, sure would appreciate if you were to subscribe to our channel here at JCSE LLC. And then I believe that there's a flag there or something that you toggle. I'm not real good at this YouTube stuff, that you can set, and that way you'll automatically receive alerts as we post new tutorial sessions. Okay, so with that in mind, let's jump into this one. The topic here is forces in double top plate splices. So this is for a timber connection. The question that we had from a young structural engineer was, do I need to maintain the continuity in the double top plate? Okay, so I'm not going to bog down on double top plate. If that's something that you don't understand, again, leave us a note at the end of the tutorial session. We'll try to point you in the right direction. Perhaps some of these things are covered in other tutorials as well. So we'll point you into the right direction of tutorials that will assist you with your particular question. Any other tutorials that are on our channel that that include W12 in their title will likely cover related topics to the topic that we're covering here now. So you can also search for those and likely find some similar concepts being covered to what we're discussing here. Okay, with that in mind, let me clear the screen. Kind of a couple of hints, I guess, that we normally go through, and that is get everything you can from these tutorials. Don't just kind of pick and choose, listen to a little bit of what you might be interested in hearing. The idea is that these tutorials are intended to empower you as a structural engineer. The idea is for you to think as a structural engineer. So the more that you can digest these tutorials and understand where we're coming from, the more it will empower you to being a structural engineer. So try not to pick off the one particular issue that you're trying to get, rather try to understand the thinking that goes behind it. Okay, in this case, we have an elevation here. All right, so this is the double top plate. This is what we call the double top plate. This is a stud. This is a stud. These are representative studs. Okay, all the studs are not drawn in. If we were to draw all the studs, then it would probably look a little bit more like this, where we would have a stud here and another stud here. All right, so what we've got drawn in there are a couple of representative studs. They are not all of the studs. There are studs that are omitted for sake of clarity. In green, you can see here, change this. You can see here, those are nails. All right. So what you have is two plates. That's why it's called a double top plate. So I'm gonna draw one line through one plate and then draw a green line through the other plate. Okay, so that's your double top plate, two plates. If this were, let's say, a 2x4 stud wall, those would be, the two plates would simply be two 2x4s, one 2x4, and then placed on top of another 2x4, and that's your double top plate. Let me clear the screen. All right, so that's our assembly here. Now, this is covered in other tutorials, so I don't want to get into how do you determine the forces that go into the double top plate, but suffice to say that there could be tension or there could be compression. The double top plate will typically serve as either your drag strut or your chord element for your diaphragm. Again, all of that, drag struts, chords, diaphragms, that's all amply covered in other tutorials that we have here in Bridging the Gap. So I'm not going to get into those. If you need help with any of that, again, just let us know at the end of this tutorial, and we'll point you to the tutorial session that covers those in more detail. But for right now, let's just kind of stay generic so that we can get to the splice, which is really what we want to cover here. So we have forces in tension or in compression as a result of the drag strut or the diaphragm chord. So depending on whether your top chord is acting as a drag strut for one scenario, or it's acting as a diaphragm chord, whether it's resisting tension or whether it's resisting compression, that is all covered in other tutorials. Just be aware that this double top plate is likely one of those elements. It's likely serving as a chord. It's likely serving as a drag strut. So it will likely be, under certain situations, be resisting compression forces, and under certain situations, be resisting tension forces. Okay, only one plate is active at a time, and that's what we want to get to here. Notice how there are splices. Notice how there, notice how there's a splice. Sorry here, guys. You know what, before I even get to that, let me do this. Notice we're going to point with a red arrow to the top plate of the double top plate. We're going to use a green arrow to point to the bottom plate of the double top plate. So now we're getting kind of into the nitty gritty of the assembly here, right? Now we're not just looking at it as a double top plate, we're actually breaking it down into its components. So the red arrow is pointing to the top plate of the double top plate, and the green arrow is pointing to the bottom plate of the double top plate. All right, with that said, now look at how in the top plate, there is a splice where I've circled in yellow. Notice in blue, I'm going to place a circle likewise on the splice of the bottom plate. Now remember, this distance can be this distance here can be easily maybe 10 feet. All right. It could be it can be 5, 6, 10, 15 feet, but it is a finite distance. After all, these 2x4s, if we're looking at a 2x4 stud wall, these 2x4s that are laid horizontally to create the top plate can't be 40 feet long, if that's how long your wall is, right? It can't be 30 feet, it can't be 20 feet, it can't be 60 feet. The contractor is going to have to splice these, put these butt into each other to create as long as the wall is. So there have to be splices. So as structural engineers, we need to be able to transfer the forces that are in the double top plate through those splices. Okay, so with that said, here is the key to the splice. Let me use this black and I will. So right there, what I'm highlighting there, what I've put the circle on, is a representative nail. That representative nail, excuse me, is the nail that goes between the splice. So it goes from here to here. So whether you specify a nail at a certain distance, might be a 16D nail at 4 inches on center. I think more typically, and this is how we would do it, we would specify the total number of nails that we want in between this splice. Okay, so this nail occurs between this splice and this splice. And the number of nails is dictated by how much force we need to transfer is being carried by the double top plate. Again, compression, tension, um, um, shouldn't say compression. We'll get to compression in a second. So let's focus on tension. Depending on how much tension there is in the double top plate, again, whether it be tension due to a cord force or tension due to a drag strut, but whatever the tension force is will dictate the number of nails. Again, how to make that calculation, that's covered in another tutorial. What we also need to understand here, and let me use this magenta, is that hopefully you start to see that because of the splice, the forces that are in the double top plate are literally jogging. They are literally jogging as they migrate through the double top plate. So here the force is being carried in the bottom plate, right? Bypassing that splice that occurs in the top plate. But then due to all of these nails that we just discussed in the splice, little by little, that force is migrating into the top plate until eventually it's all in the top plate, thus bypassing the splice in the bottom plate. And then this whole process reverses. Then there'll be a bunch of nails between the next two splices so that the load then migrates into the bottom plate and thus bypassing the next top plate splice. So with that, what we're saying is that in a double top plate, only one plate is active at any one time. That's why sometimes our forces are so large in the our cord force or our drag strut force is so large that you'll see that we put in three plates. So instead of having a double top plate, we'll have a triple top plate because we need 2 plates to be active at any one time. One plate alone will not handle all of the tension that we need to resist. Now, the reason we bypassed compression is because compression kind of takes care of itself. Compression, as long as these ends are butting into each other, right here, right? As long as they butt into each other, then the compression force will transfer from one plate to the other. It's tension that we're a little bit more concerned about in making that load transfer. Okay, so with this, let me clear this screen. Let me move on down. So we've covered this concept. A steel strap, sure, because sometimes, um, especially in a situation where we arbitrarily are cutting, and this might happen more typical when it's an existing double top plate. So let's assume this is an existing double top plate, and for some reason, we come in here and we have to create a cut. We have to splice this. Maybe we're splicing one of the plates or the bottom plate or both. Really doesn't matter, because the reality is that once it's in place, it's probably going to be very hard to see whether at any point where we're creating a splice, whether the splice is in the plate that is active or the plate that's not active. That's hard to see in practice. So we just assume that if for whatever reason we're splicing a plate, whether again it's the top one, the bottom one, or we have to splice both of them, we just assume we're splicing through the active plate. So we have to determine what the tension force is that is in that double top plate, either due to a cord force or a drag strut force. And then likely we need to provide some kind of a steel strap, um, to be able to transfer that tensile force. Usually what we'll do, usually, at least our first option, is to nail a strap to the side of one of these plates or both of these plates. So we might put a strap across that splice. Again, we might even double it up. Undo that. We might even double it up and put a strap on the bottom plate as well. And the strap will then transfer tension across that splice. The size of the strap, the number of nails will be dependent on the force that's in the drag strut or the cord force that's being carried by the double top plate. Okay, let me clear the screen here. Let me scroll down. Okay, keep in mind, what we're not showing here is the actual, let's say, wood structural panel, the actual floor or roof assembly. Let's assume that this is framing here. All right, there's framing here. So the sheathing, the actual sheathing is probably right up here. Point is, this element, the double top plate, that double top plate is in close proximity to um, that wood structural panel, okay, to the sheathing, to the diaphragm, right? Again, the whole concept of a diaphragm and the chords of a diaphragm, that's another tutorial. So if you need help with that, that's not clear to you, let us know at the end of this tutorial and we'll point you in that direction. But clearly your cord on your diaphragm has to be in close proximity. I might have said that redundantly. The cord has to be in close proximity to your wood structural panel, to the wood structural panel, to act as a diaphragm. Okay, so so that's assuming that that's the case. Now let's clear the screen here and let's take a look, I think, at another assembly where that's not the case. And this, you'll recognize, you might be able to recognize this is an elevation. This is something that happens in practice quite frequently, right? So now take a look. Now we've got our double top plate down here. What we're not showing are the full height studs. So the full height studs will extend down this way, right? Here's our stud wall. With the yellow arrow, I'm showing you the double top plate of the wall. But in this case, it is a gabled roof. So the roof is actually has a profile where it rises and gets up to a crown and then slopes down in the other direction, right? The double top plate stays constant at a certain elevation, but the roof assembly, which would be all of this, right? On the roof assembly, actually is changing in elevation, rising as the profile of the roof, as the roof with the profile of the roof. So this is a situation where now the double top plate is not in close proximity to the wood structural panel sheathing. Therefore, it can't really serve the purpose of the drag strut or the chord element for this diaphragm. Again, I believe that's covered in another tutorial, so I'm not going to get too much into that. But now we have to look for another element that is closer in proximity to the sheathing so that it will act as the diaphragm chord or diaphragm drag strut. So in this case, it looks like we have, it looks like we have some kind of what we would call a rim element. There is a rim element, maybe a rim joist. Looks like there's some lumbar piece that is immediately below the wood structural panel sheathing. And that is our likely candidate and what will behave as the chord or the drag strut. So now we just have to make sure that this element then has that capacity, right? This element has the capacity to resist that tension, that compression, depending on which analysis we're conducting. But then we get back into that splice situation where clearly, I should have, you know what, let me draw this differently. Let me draw this with magenta. So now this is one element, right? And then the one shown in blue is another element, right? That can't be the same piece of lumber. That somehow has a kink there. So this is one piece of wood, one piece of timber on the left side, one piece of timber on the right side, and they're transferring tension. So what happens at the splice? They're just going to separate, right? They'll just pull apart. So again, we're back to our solution that we discussed a little while ago. We need to put some kind of strap. In this case, we can probably put it on top. Really doesn't matter whether we put it on top or we could even sometimes, I think depending on whether the forces are small, if they're small enough, we might put a strap here on the side to try to connect those two to keep them together. Like I said, we can place a strap on the top, or sometimes I think we can also, what we've done is like literally break a strap, break it and weld it, or weld two separate straps, right? So we will end up with something that follows the contour of that rim element, right? So it'll be a strap that looks like this. And then, oops, I didn't do this right, huh? Well, this probably should be more of a vertical line. And then another strap or the same strap that's broken in half and then re-welded there at the middle so that we can elongate this and follow the contour of this rim element. Okay, so a couple of different ways to handle the splice of a chord or a drag strut of a diaphragm. Let me see if with that we've covered everything that we want. Let me clear the screen. Let me see if we've covered everything. Yeah, right. What acts as the chord? So in this case, the chord we have to use kind of some reason, no, we kind of need to be reasonable. You know, again, in this case, the double top plate is so far away, by so far away, you know, it's several feet, kind of unreal, and separated by studs or cripple studs. You know, it's separated by these cripple studs, that the reality is that chord forces aren't going to migrate all the way from here where they're generated in the sheathing down to that double top plate. So we need to find something that's in closer proximity. And in this case, we found it with this rim element. Okay, it needs to be in close proximity to your sheathing. Okay, let me clear that. So the strap offers another method in which we can splice our cord element to transfer tension forces. Again, whether the tension is generated by drag or by cord, either way, it's a way to transfer the tension across the element, which is typically a double top plate, but we've seen now scenarios where it doesn't have to be the double top plate. Okay, so with that, we're done. Again, appreciate if you give us a thumbs up if this was helpful to you. Appreciate any positive comments. Heck, don't mind negative comments. You know, if you have some constructive criticism, by all means, please let us know in what way these might be more helpful to you. And if this was helpful to you, then subscribe to our channel and click on the flag or whatever it is that will alert you when we upload any other structural engineering design tutorials, so that you can gain better traction, quicker traction in your career. Okay, real good, guys.